Welcome to episode 337 of CppCast, the first podcast for C++ developers by C++ developers. I'm host Rob Irving, joined by my co-host Jason Turner. Jason, how you doing today?
I'm all right, Rob. How are you doing?
I'm doing all right. My son turned 13 today,
Yes.
so I am feeling a little old from that, but I'm doing okay. And
That
he's
means
doing
we've
good.
been doing this podcast for more than half of your son's life, it seems.
Yeah. Wow.
Does that make you
That is
feel
true.
older again?
Yeah, it does. How about you? Got anything going on?
Well, I just had that moment myself when I released episode 311 of C++ Weekly, which, as probably a lot of our listeners know, I have not missed a single week. So knowing that I've been doing it for 311 weeks, at first I wanted to feel a sense of pride, but then I just felt old instead. So,
Yeah. All right. Well, at the top of every episode, I like to read a piece of feedback. We got this message on Discord from Eli or Ellie saying this is not a very important piece of feedback, but I like it a little better when you let the theme song outro play for longer before starting the podcast audio proper. I think it might be because the first minute and change of every podcast used to be exactly the same, and it became sort of comforting for me to follow along with that. So yeah, we did start using Editor recently, and I guess they just did a little bit of a different style with editing the intro music with the intro of the show. But I will pass on that feedback to the editor because there could be other listeners also a little, frazzled by change. So
did we actually talk about why you're using Editor now on the
I'm
podcast?
not sure if we had on the podcast, but we have had a Patreon for a while for the show, and we put out a goal when we first opened up the Patreon that if we ever get to a certain level of support, that we would start using Editor as opposed to me editing the show myself. And we did hit that goal earlier this year.
And it's starting to work out.
Yeah. Oh no, I think the editor's been doing a really great job. We did switch editors. I won't, complain about the other one, but yeah. The new one we like. They're doing a great job.
Good.
All right. We'd love to hear your thoughts about the show. You can always reach out to us on Facebook, Twitter, or email us at feedback@cppcast.com. And don't forget to leave us a review on iTunes or subscribe on YouTube. Joining us today is Howard Butler. Howard is the founder and president of Hobu Incorporated, an open source software consultancy located in Iowa City that focuses on point cloud data management solutions. He's an active participant in the ASPRS LAS committee, a project steering committee member of both the PROJ and GDAL open source software projects, a contributing author to the GeoJSON specification, and a past member of the OSGeo board of directors. With his firm, Howard leads the development of the PDAL and Entwine open source point cloud processing and organization software libraries. Howard, welcome to the show.
Yeah, thanks for the introduction. Excited for the opportunity to talk about geospatial stuff and C++ with you guys.
Yeah.
How did you decide to create a company founded on open source stuff? Because that sounds risky to a lot of people, I think.
There wasn't a decision so much as I was doing consulting, and my wife and I moved towns. We moved from Ames to Iowa City, and part of the job search, I wasn't doing so well finding kind of what I wanted to do for a job, and I'd been very active in open source geospatial software. And so I thought, well, maybe I can just try to make a business out of doing this, where people need features added to software or support and capability or help navigating the community. And so I started the consultancy doing that. It was kind of like a moonlighting sort of thing, and eventually it just we started developing software in the point cloud and lidar domain, which was at the time was a very small niche. It's grown quite a bit now, but
right.
And so people would find us to add capability to the software, and they were building systems with our tools, and so the business just kind of grew from there.
How long ago was that?
So Hobu actually started as like a consultancy maybe 20 years ago, but we started doing very heavily focused on open source and lidar stuff in 2008 and 9.
2008, 9. Okay, cool.
How big is the company now?
We're 5 employees and have 1 employee in Peterborough, New Hampshire, and then the rest of us here in Iowa City. And yeah, always
Very
looking
cool.
to find good engineers like everyone else. But
So you are hiring right now?
of course,
We usually ask at the end, but
everyone's unicorn hiring, right? Unicorn hunting.
it does seem like it's verging on impossible to find new programmers right now because everyone has a job that they want, or there's not enough people or something.
Mm-hmm.
Yeah, I also think, we're in Iowa, which is kind of a challenging environment too, just because there isn't as big of a community. And so, the buy or build solution is mostly build, right? You want to hire young engineers and mentor them forward, either in your development practices or teach them the culture that you're trying to get them to participate in, and then they grow up and leave, of course. But that's one way to move forward with trying to get the talent that you need.
Right.
All right, Howard, we got a couple news articles to discuss. Feel free to comment on any of these, and we'll start talking more about these geospatial libraries that you're involved with, okay?
Sounds great.
Okay, so this first one is Swift and C++ interoperability workgroup announcement. And I had not heard of this, but we had a listener reach out to us over Twitter, Jason. Actually, I think listener and former guest telling us that we should talk about this one. And yeah, it seemed really interesting. The Swift development is going for bidirectional interoperability with C++.
Yeah, I mean, examples here are things like standard string and standard vector without having to go through a memory copy C
Right.
binding layer, which is generally what has to happen with other languages like Java, Python, whatever.
Are there other languages with this type of interop?
As
I'm
far
not...
as I can recall, only D from what
Okay.
Alex Andrescu told us when he was on, because he was talking about basically when D and C++ interop works by relying on knowing what the calling conventions are for the C++ compiler that you happen to be trying to interop with.
Mm-hmm.
And so that's really getting into the guts of things there. It's the only other language I know of that does that.
Seems really cool. And I don't think we've ever talked about Swift in any detail on the show, but maybe this is a good opportunity to try to get someone from the Swift community who's involved in this C++ interop, because it seems really cool.
Yeah.
You have any thoughts on this one, Howard? Do you do anything with other languages that maybe interop with C++?
Certainly, the libraries we develop have interop with things like Python, done some Java. The bindings approach of doing that is always pretty painful for everyone. Somewhere across that boundary, somebody gets to be responsible for who owns what when, and that always is the problem. So things that make that better would always be exciting. I don't know that. There's never really been a silver bullet for it though. Like every kind of generation has had its own sort of approach to doing that kind of interop, and it always ends up being a compromise in places that you don't want, and then it kind of gets redone the next generation in a little bit different way with the slightly different compromises, and you're kind of back in the same spot.
It was all these kinds of issues is why I created ChaiScript in the first place, because I wanted a scripting language that was designed for interop with C++. And just for the record, I don't maintain it anymore, so I'm not trying to convince anyone to use it. It cost me far more money to write and maintain it than I ever made from it.
All right. Next thing we have is another post on the Old New Thing, Raymond Chen's blog. And this one is a mystery of the crash that seems to be on a stood move operation. Could you go over this one for us, Jason?
Oh, I love this because even though I had already read the article once, and when I came back to it to review before the show, I'm like, forgot where the crash was. But what it comes down to is that the programmer is using an object and moving that object in the same statement. And that was unspecified behavior before C++ 17. And the way they're doing it because they didn't know which, there's no guarantee as to what order these things are going to occur in. In C++ 17, there is the guarantee that the function itself will be resolved first, and then its function argument will be resolved, but there's still no guarantee as to what order the function arguments will be instantiated in C++ 17.
So would this
But
code be okay in C++ 17, or is it still not a good
that
idea?
code would be okay in C++ 17, yeah. But I mean, not that it's good code, I would say, just for the record, because it still feels a little sketchy. Like, you have to know exactly what the rules are saying right here to have any real clue what it's doing. That's how I feel about it.
All right. And then the last thing we have is another post on the Visual C++ blog. And this is how we use C++ 20 to eliminate an entire class of runtime bugs. And this is a good article. Basically, goes down to formats, compile time, checking support, being able to just get rid of tons of possible bugs with their format strings in the Visual C++ compiler.
Yeah, but how this is actually implemented,
Mm-hmm.
I think our readers should just go and read this and like let it soak in for how it works.
Yeah, we'll definitely put the link in the show notes for our listeners to go read through it. Definitely a good article. All right, so Howard, let's start off by talking about what is the GDAL library. I don't think we've really ever talked about any geospatial libraries before on the show, so I think it should be a new topic for a lot of our listeners.
Sure. So GDAL or GDAL or GDAL, you might hear it pronounced lots of different ways in many different languages, is the Geodata Abstraction Library or Geospatial Data Abstraction Library. It was started in about 1998 by a guy named Frank Warmerdam. Frank had developed a software package, or the engine of a software package called PCI at his former employer, and it was allowed people to do raster data. So raster, just array data. If you hear me use the term raster or vector in geospatial, they have kind of geospatial meanings. But PCI allowed a user to process and manipulate raster data in kind of an engine, and so it allowed people to construct workflows, and they could manipulate data, change formats. And so Frank had developed PCI, and it was proprietary. His employment situation changed, and he decided, well, I'll make PCI version 2.0, except it'll be open source. And of course, the 2.0 version of everything you ever write is always better than the 1.0 version. And so he started kind of developing this, and his business model at the time when I met him a number of years later, he said, well, I wanted a business model which was, he likened it to being the garbage man, and what he meant by that is there's a set of tasking that is convenient to outsource or contract out, and format translation is one of those. Like, nobody likes to write formats translators, be responsible for them, have to worry about all of the impedance mismatch that goes on with taking data in one system and moving it to another. And so he saw this as kind of like a business opportunity, in that he could make a living developing these translators for people and then add processing capability to it. And so his business model was actively doing that until about, I want to say 2010 or so. And or maybe 2000, something like 2010, a Google recruiter email finally landed for him, and so he started working for Google for a little while. And then now he works at Planet Labs, which he was part of the team that helped process the data. Planet Labs acquires satellite imagery over, the goal is everywhere on the Earth every day, right? And so big geospatial data processing backends and engines. And so GDAL or GDAL sits underneath all of this. And so Frank developed it, and it kind of took on a life of its own as other open source and commercial software products started to pick it up and use it as that kind of underlying engine, conveniently for format translation, but then as more capability they needed to add to their software, GDAL became more capable as well.
So it's primarily a library, primarily like a command line tool. Like, how do I actually like work? What do I feed it, and what do I get back out from like an API programming perspective?
So yes to all of those answers. So
Okay.
it's a command line library, or excuse me, command line utility. It's actually a set of utilities that start with the name. GDAL is the prefix, and then a bunch of different names that kind of do different tasks. It is a C API that sits on top of a C++ API that provides kind of an ABI stable layer for people to write software against.
Mm-hmm.
Although the C++ API hasn't really changed that much over the years either. And then it's a C++ library that people can program directly with. And then there are kind of two legs to the library. There's the raster, which would be array and imagery and image processing, and then the vector side, which is called OGR, which is points, lines, and polygons. And those APIs were kind of merged together, at least at a really high level, maybe about 4 or 5 years ago. But most programmers kind of will specialize depending on what major data types they're working with. And then there's kind of a virtual layer. Well, there's two virtual layers. There's one virtual layer, which is kind of a virtual, it's called VFS, or a virtual file system layer that abstracts away data access, network file access, and is something that a software engineer can write to. And then there's kind of a workflow or a directed programming language called VRT, which I used to stand for something, but it's essentially kind of an XML mini language for orchestrating processing workflows to do various things to data, so that you don't have to realize that data by a full IO step or a full process. You can simply just describe it as a process and then execute it in one shot.
Okay. And you mentioned there the raster and vector data models, and just make sure our listeners understand what we're talking about. So raster, you said imagery, and we're talking like that satellite imagery that you were mentioning before.
So PNGs, JPEGs, TIFFs, of course, those would be most common and commonly seen. But there's nearly 200 raster format drivers in GDAL. So
wow.
Every little weird software developed its own little format somewhere, and now it's like it's from 1970s NASA data that you're reading, or it's it was a small commercial product that existed for a little while, and it had a slight and little unique format. And so again, the idea of the library is to provide support and capability for people to have abstract access to that content and be able to take that and do other things with it. Now that task is messy, right? Like the content, the pixels themselves might mean different things in different formats. The metadata or information that describes what is those pixels might be different across all of those formats. In some cases, the library tries to handle some of that, but it can't in all. And so, that's often left to the user to manage that as they might go from one format to the other. That said, there's probably 3 or 4 like very common geospatial formats, and that you'll see most data in. So one is TIFF or something called a GeoTIFF, which is just a regular old Adobe TIFF file with some geospatial metadata. You'll also see the JPEG family of raster data, so JPEG 2000, and various flavors. And then there's the HDF family, so HDF and NetCDF, which are they're open source format containers that allow people to construct binary representations of data. And you'll see that very commonly used in meteorology and space applications. So you'll find HDF and NASA and stuff like that quite commonly.
And then you said over 200 raster formats. Go ahead and describe what you've got going on the vector side too, then, I guess.
So on the vector side, there's not 200 of them. There's certainly more than 30. The commonality there is points, lines, and polygons, and then attribute data, which would mean that those columns of data or the table of data that might correspond to every one of those features or geometries in that data source. And that world has its own kind of common format base as well, or commonly used formats. So you'll hear the phrase shapefile, which isn't actually a file; it's a group of files that came out from a company called ESRI or Esri in the 90s. GeoJSON is a specification that's out there that's frequently used for data interchange in web contexts. Not particularly efficient, but super convenient.
I was wondering why wasn't GeoXML or GeoYAML when I saw it in your bio here.
Well, I don't
I'm not really being serious.
There actually is a GeoXML, and
okay.
But it's not called GeoXML, it's called GML. And when XML was super in vogue in the late 90s and early 2000s, there was a lot of modeling in the geospatial realm to do that around XML and through an organization called the Open Geospatial Consortium. And so there are very detailed 1,000-page specifications about doing GML. Very, very complex. If you've ever had to implement GML, I'm sorry for you. In the end, most people just want the point, line, and polygon, or what you'll hear the phrase simple features, right? They don't want a complex ontology of geospatial modeling. Like very few applications need all of that. And if your application needs that kind of thing, then you're going to have to support it with a lot more engineering than hoping to just off the shelf a standard.
No,
So I was just going to say real quick, on the GDAL website, there's a list of software using GDAL, and I'm guessing a lot of our listeners have at least used an application that is using GDAL, like Google Earth. I'm sure a lot of people have used, but it seems like there's a whole lot of others too.
Yeah, and then a lot of the back end, server side geospatial computing too. Most of the mapping companies use it in some form, at the very least for data translation, if not some of the algorithm and processing. There's people putting it on phones. There's people putting it in. There's a WebAssembly and there's a browser-based implementation that people have kind of been working on to do to pull some of the processing algorithms up to browser land. So it's kind of going all over the place, just like computing's kind of going all over the place.
I couldn't remember what I was going to ask a second ago. How do the vector and raster worlds meet, or do they?
So I guess my supposition is they meet at point clouds, which is what we do. Which is, point clouds is simply just a bunch of points, but they're modeled as discrete locations in space instead of an array of pixel values or an array of points like a raster data might be. Okay. Point clouds have properties of both. Like you want to manage them in raster ways as much as possible, meaning you want to address them conveniently. You want to compress them as efficiently as possible. You want to transmit them and model them simply, but you also want all of that fidelity of that point cloud corresponding to things like where it's located. Maybe you have some other information on per points, like say you had a laser scanner and it was measuring a returned intensity or other information that you might attach to, like a LiDAR point or something like that. And so kind of in some ways, those point clouds are kind of in between, at least in the geospatial realm. Another area where all of these kind of meet together, and when I talk about PDAL or POODLE and what it brings unique to the kind of the point cloud space is the geospatial part. And so the geospatial part here for raster, vector, and point cloud is coordinate systems, the modeling of that coordinate system in the where part of it. So it's not simply just a coordinate, that describes some point in some space. It's a coordinate that describes a point in world space or other world space if you're doing maybe NASA stuff or something like that. But being able to model all of that coordinate system information, be able to transform between those, that's where all the kind of the stickier parts of geospatial tend to be, just because it's necessarily complex sometimes, and also because most people don't want to have to think about it, and want to be able to outsource that to software libraries that can do that for them. So GDAL depends on a library called Proj, and so Proj is an open source library that originated in 1983 from a guy named Gerald Evenden at the USGS. And so there's a very famous book out there, the Robinson book from USGS, that described a whole bunch of coordinate system transformations and coordinate systems. And so Jerry implemented a number of these in the personal and mini computer era. And so this library kind of survived as a C library over the years as he was developing it. He retired in, I want to say 98 or 99, around the time when Frank Warmerdam was doing GDAL. And so Frank needed a coordinate system support library for GDAL, and so he used Proj as the basis of that. And over the years, so Proj mostly concerned itself with just the mathematics of geospatial projection, and it didn't concern itself with geodetics, and which is modeling the Earth. And so recently we had an effort to update the Proj library to support a geodetic transformation engine. So applying the math and the modeling of geoids and datums and things like that, so that people can do very precise engineering activities with this geospatial library, instead of making a web Mercator map for the web or something simple like that. You can do that stuff with it too, but being able to have the capability to do this complex geodetic modeling for 3D.
I wonder if it's worthwhile just for a moment to make sure our listeners know what we're talking about with projections. I think you just said web Mercator, so we're talking about like different ways of projecting Earth coordinates to a map.
Yep. So, a while ago there was the orange peel story where, you try to take the orange peel and lay it flat out and draw a map with it. And if you take a geography 101 class, you might get to do that as well. It's a lossy operation no matter what you're trying to do. If you log into Google Maps, maybe 5 or 10 years ago, the projection or the coordinate system of the description of that map is something called web Mercator. And it was kind of a special thing that Google had made as they part of developing Google Maps. And it's kind of a shortcut over something that's called Mercator, which of course is a very well-known coordinate system. As a data modeler, you have to make choices about your coordinate system depending on what you're used. So, you have the ability to preserve area, direction, or angle, right? And so you can't do all three of those at once. And so depending on what you want to do with your data or how you want to model it, you'll have to make a coordinate system choice. And there's lots of them to choose from. And you'll see them used in various contexts. There's definitely some very common ones. So your GPS on your phone, for example, is going to be just in geographic coordinates, or plate carry, which is latitude, longitude, or longitude, latitude, depending on who you want to argue with.
Okay.
Oh, I hear, raster, point clouds, geodesic. You mentioned LiDAR earlier. I start thinking, you did mention LiDAR earlier, right? Okay. Just like, I start thinking like, people that are doing like archaeological surveys and photogrammetry, reconstruction of scenes and that kind of thing. Does that have an overlap, or have I gone too far?
Definitely an overlap.
Okay.
Definitely an overlap. So, there's the group of archaeologists who are, flying LiDAR in Central America to be able to look for lost cities and stuff like that. And, that LiDAR doesn't penetrate the foliage. It's just you're shooting so many lasers at such a high frequency that if there is a ray that can cast through the foliage to hit the ground, you try to do that with it, and then you spend a bunch of computing to process it back out, right? And the photogrammetry-based point clouds is where you're taking lots and lots of photographs at lots of different angles and doing various stereophotography processing techniques to extract out a 3D scene or a 3D point cloud from that data, and then build a 3D model from that. So sometimes you'll have lasers, actively scanned lasers and LiDAR to do that, but you don't need that to do it. So if you're just out flying your drone or whatever, you can put that through various open source software to be able to construct an orthophoto, or like a photogrammetrically correct raster image. So there's a software project out there called Open Drone Map that you can use to do that. But you also extract out this 3D scene point cloud, right? And other associated things. And so again, it's all kind of the same sort of story of lots of data, compute out a geospatial product, and then take that geospatial data product and go do whatever you need with it.
I feel like, because I'm just trying to wrap my mind around where the edges of this tools are, and the original goal you said of the person who originally created the stuff was to be the garbage man that just did the image the translation that no one else wanted to do. But it sounds like you do a little bit more than that now, because you can also do processing and alignment of points, perhaps. Is that
yeah? So GDAL grew over the years. GDAL grew the ability to do warping, which is taking that raster, taking that array of data and stretching it or rubber sheeting it over a bunch of points, and doing that in various ways depending on what the needs are. And so that's a task that you need to be able to do to, say, take these raster data and transform them in different coordinate systems. So warping is a common one. Compression, there's large flavor or diversity of flavors of compression, and depending on your data type, this may or may not have lots of meaning for you. One thing that the geospatial data almost universally has in common is it's large. And so maybe it's not so dense in content, but it's very what I always say is it's very fluffy. There's just lots of bytes. And so sometimes it compresses well and other times it doesn't, but a compression is a huge part of any story with geospatial data.
I like the idea of fluffy data. Never heard that before.
Yeah, like big data is. Yes, it's big data. Maybe it was one of the original big datas, but that the meaning of that phrase is kind of smashed out a little bit, and it's a little bit like cotton candy.
So you were talking about Poodle and Goodle or GDAL, and so is Poodle part of GDAL, or is it a separate library built on top of it?
The latter. So we started developing some point cloud software, like I said, in about 2008 or 9. And this point cloud software was using GDAL to provide some geospatial capability like coordinate system transformation. We were doing some filtering, geometry filtering and stuff like that. And then we started developing a library called liblaz, which was the first open source library that was available. And it was clear that liblaz was focused on this LAS format, which would be kind of like the TIFF of geospatial LiDAR, for example. And which was
question.
Yeah.
I think of TIFF as the over-engineered image file format, and I'm wondering, when you said it's like the TIFF of geospatial, is that because it's very it's very configurable and has lots of options, or just because it's ubiquitous?
Mostly on the ubiquity thing. Right? Okay. So it would be, TIFF is kind of like a primary sort of geospatial raster container. I agree with you on the people write really horrible TIFF story. But, just in terms of ubiquity and frequency or commonality in the industry for geospatial point clouds, LAS is kind of that format. But there are other formats. And so it was clear we needed some kind of abstraction API that would provide a similar sort of capability or space as GDAL. We wanted the ability to have an abstract data API so that we could provide access to the content without necessarily imposing all of the complexity of the organization on the user, right? So in exchange for that, you might be a little bit slower, or you have impedance mismatch, but the ability to just get those points out and go do something with them in your application, if that's really valuable, we needed to be able to do that. And so we developed that primarily for doing point cloud data warehousing, right? So there's lots of companies and governments out there flying LiDAR over places like Central America, but they're doing it all over the United States or all over Europe, and they're using this information as kind of geospatial based data for things like flood mapping, 3D modeling, photogrammetry, and so there's kind of a bucket where all that stuff gets dumped, and our software kind of sits for one of those buckets. Our software sits there and does all the processing for it.
So is there like a knob that you can turn and say, I want slower processing, but like super precision conversions, or, I want faster processing, but, quicker results so I can just visualize the data real quick?
So for raster data, that knob is to kind of overview or map the data into a pyramid. And that's your kind of common processing technique for imagery. For point cloud data, that sort of map is going to be some sort of indexing structure. So commonly you'll see an octree used as that filtering technique, where I want to select the data, but to a specified resolution. I don't need 250 points per square meter or whatever that original data capture was that allows me to model the surface so intensely. I don't need that to maybe ask and answer a really quick question. And so you're seeing data organization that's doing those kinds of processing techniques to allow people to touch that data at rest without having to process the entire thing at once.
That octree is what Carmack famously used in Quake to be able to do software 3D rendering. Is that right?
Yep.
Okay.
So yeah, computer graphics 201-ish sort of techniques. I mean,
although it was groundbreaking when he did it.
Right, but like that capability is I mean, those are the hammers you have in the box to be able to go do stuff.
Very cool.
Sounds like there's just an awful lot going on here in your world.
Yeah. And it's been a world that was kind of the domain of what I would call governments and government data capture. LiDAR was, it cost $200,000 for a laser scanner that you could mount on an airplane maybe 15 years ago. And it was just a really large capital investment to capture and do stuff with this kind of data a while ago. And you have a LiDAR on your iPhone 12 Pro now. You can walk around and capture point cloud data.
Really?
Yeah.
I did not realize that.
There's a laser scanner on your iPhone, and people are building applications to do things like augmented reality, where they want to make digital representation of their scene or their environment and put that into their goggles, or put that into photographs, 3D photographs or whatever. And so the data type and the data to support that is the same stuff, right? It's geospatial, it's rasters, it's point clouds, it's meshes about the space. And so these processing techniques, even though they're 20 and 30 years old, are still applicable today.
Oh, okay. I'm reminded of, I think tangentially, although maybe it has more of a direct relationship than I'm aware of, OpenStreetMaps, which I saw a recent article that's discussing like how all of the world's companies, trillion-dollar companies and world's governments all rely on OpenStreetMap for their GIS kinds of things right now.
For the base. Yep, absolutely.
Yeah.
Yep. And in my opinion, the ones that are a little bit more progressive are the government entities, and at least that are a little more progressive, are embracing that as the place to have lots of impact with their data that they would produce. Whereas, and previously a government would spend a lot of money constructing that data. So in the United States, we have, Census Bureau does that, right? So the Census Bureau needs to know where everybody is so that they can find them all to do the census. And so part of that tasking was to build the street addresses and build the maps of all of the streets. And, then companies would take that and go do stuff with it. Some of these organizations, though, they're embracing OpenStreetMap and pushing that data out to that map or out to the common database early in the process instead of trying to do it later on, so that it has more impact, has more utility, and it's a lot more up to date, right? Because it's just something that's necessarily always changing.
Yeah, I 15 years ago went on vacation to Ireland, and at the time, all of the tour info, travel info said, you can't rely on GPS, you can't rely on a map that you buy in the US. You have to buy a physical map in Ireland when you get there to know what the roads are doing. I'm hoping now that that's changed, as you said, with people getting more pushing data to OpenStreetMaps and embracing that.
Some countries were a lot, there's variation in the policies too. So the United States, for example, has open data policy where, the data it captures tends to be open and available, and companies can use that to build products and make things more valuable if they want, and take that and close it up and enhance it. In EU, it wasn't quite like that. Certainly 15 years ago, I think things have gotten better. And then just everybody's geospatial view of the world kind of starts with their phone nowadays. And so that might be, Apple Maps or Google Maps or something like that. But then, they're starting to take that into other spaces. Like, I know Snapchat has a bunch of geospatial stuff that they're doing. I don't know if TikTok's doing any geospatial stuff, but the spaces are kind of converging where this like digital space and physical space stuff kind of starting to merge together a little bit. And, the part that takes the reality, the physical part, and puts it into digital is challenging data processing, challenging data modeling and software.
So I wanted to kind of ask a little bit about the C++ code in these libraries. I'm guessing the answer is going to be very different whether we're talking about GDAL or PDAL, but are we using modern C++ at all in these libraries? It sounds like GDAL is a very old library and PDAL is maybe relatively new.
Yeah, GDAL predates good STL.
Okay.
We actually had a policy in GDAL where we wouldn't allow STL into the library. Like GDAL had its own kind of STL thing going on. And there's still quite a bit of that in the code base actually, but I think standard string and standard vector are allowed at least.
All right, hold on, I'm gonna make a fork and start a pull request now.
I think you would describe the design of GDAL as like, that original sort of vision of C++ of C with classes and not much more than that. A very simple kind of core API, top level API, and then the concept of that GDAL calls drivers, which are just essentially implementations of a particular data model applied to the overall GDAL model. What that's allowed is for people to contribute to the library and only have to focus on the part they care about, which is modeling their one specific little format or their one specific use without having to worry about I think it's almost 1 million lines of code now. The big complexity of this library, they don't have to worry about that if they want to just focus on their one little task. GDAL, I guess what I would call it kind of fluffy or verbose in terms of style. It's not particularly compact. A lot of the reasoning for that is, in the late 90s, early 2000s, compiler variability was a lot bigger. GDAL expects to run on, it was running on everything from AIX to Windows 32 to, OS 10, first flavors of OS 10. So it was running all over the place. And so that it had to assume the responsibility for all that compiler variability. Things have improved a lot in the interim. So when we started Poodle in 2010 or so, Clang and GCC were, implementing modern C++ at that point. C++ 11 was just kind of coming onto the horizon. And so we were able to say, hey, we're going to cut our baseline here at C++11. Eventually, our first implementations were based on Boost, but once C++11 compilers were prevalent enough that you could depend upon them for the platforms you cared about, we set that as our floor. And so, that gives you things like shared pointers and memory management and stuff like that. Recently for PDAL, though, the next upcoming release, we're setting that floor at C++17. The thing that pushed us up there is standard file system, and getting that universal support for that across everything. I think the deployment targets for where our software goes tends to lag, just because of the open source community. The packagers or the vendors like Ubuntu or Debian or Red Hat that would pick up these libraries, are quite conservative, right? And so the compilers they have available to them by default are conservative. Their settings tend to be quite conservative because their customer base and their user base wants things to move slowly so that stuff doesn't break. And so that for us, that has to be kind of a target of, we're not going to turn C++20 on, for example.
Yeah.
Even though as a developer we would love to, and so we both of those libraries kind of track that migration or evolution.
Okay.
What kind of performance considerations does this system have? Like, are people like relying on it being super performant?
How do I say this? In some cases, maybe. I mean, there's a penalty for having an abstract API, right?
Right.
Is you have this penalty of transferring between your data models potentially, and if you write purpose-built software for a purpose-built format, you're going to beat it. And so the idea with these libraries is if that's not a consideration for you, and you as a consumer of the content just wants access to the content without regard to those high performance considerations, you can get away with that, then libraries like these are quite valuable because as a developer, you don't have to worry about all the intricacies of how data was laid out, and then they roll a new version of that format out, and now you have, more complexity to deal with, and so in exchange for that, the bargain there is that as a consumer of the content, you don't have to worry about all those intricacies. But if you need performance and you need to manage your system very precisely so that you know what's going on all the time, you're just going to do much better developing and controlling that yourself. And then you might provide a driver, say for GDAL or for PDAL, to allow people to access your thing. And so, we see lots of companies will do that. They might even be closed source, so they'll have an SDK for their format, but they'll provide a GDAL driver for it so that people have access to it. There's lots of benefits to that. One is GDAL is as kind of a distribution platform for capability. GDAL is available on Ubuntu and Red Hat and Conda and all over the place. And so people will install it and use that as kind of a base for stuff that they're building. So having support for your thing there has some value to it. And also that allows you to manage the life of or the features of that thing without regard to this larger thing. And so you can kind of control how those move together.
Okay. So I've got a couple of follow-up questions I've been thinking. Like, you have 200, 300-ish, whatever, different formats that you support between the raster and the vector, right?
Yeah.
Are all of those parsers then written internally, or do you ever rely on like libpng, libjpeg, those kinds of things as well?
So frequently we rely upon libpng or libjpeg or libtiff or lib whatever, or proprietary SDK for weird one-off format that 3 people use, but is really important to some group. Like you'll see that all combinations of that. So GDAL and PDAL both allow a user to build a proprietary dynamically loaded plugin that'll get woke up at runtime that they can adapt the API to their driver. And so that's been an important part of the model of both of these libraries, in that we recognize and want people doing proprietary software to adapt to the system in a way that is opt-in when they want. They don't have to make some bargain to be able to participate. And we've seen companies that will do that, and then eventually, like, it's more convenient to just have an open SDK, and then eventually it's just more convenient to have it into GDAL or PDAL. And so we've seen some of that go on as well. But every company doing various things can make their own business choices or technical choices to do that, and they have the flexibility within the system to manage that.
So how much of these different drivers with supporting up to 200-300 formats, how much of it is in the GDAL code base, and how much is like third-party drivers that you could optionally put in if you have it available?
So if you go to the website and kind of list the raster drivers, I think there's like 180 or 200 or something. I don't know what the list is right now. The majority of those are kind of adaptations on the same thing, which is a bunch of binary bytes laid down on disk with some metadata. And so they might have different organization, they might have slightly different meaning, but like that's the gist of what raster data is, right? It's just a bunch of bytes on disk and something that describes how they're organized. And so those drivers, those format parsers tend to be pretty simple. They don't have to be super complex. They don't have lots of options or features with them. But then there's others that are. You'll see things like JPEG 2000, which is a really complex specification for compressing raster data. And there's a library called OpenJPEG or that's available to manage that. And GDAL will just delegate and use that as the library, right? So it doesn't do the decompression, it doesn't do the geospatial part, it just adapts that model to GDAL's model. And so some of the drivers are that. You'll see proprietary drivers as well. And what most vendors will do is they'll include that proprietary driver or parser or implementation of what's using their SDK in the GDAL project itself. And then they'll have the user, whoever it is, essentially compile and link that when they're building their own GDAL to make it available to their customers. And so that's another model that's available. And then finally, the last model is we just provide a runtime DLL that's linked against GDAL, and you can load it up at runtime to get access to our format along with either our SDK or whatnot. And you'll see that commonly done as well, mostly in commercial software deployments where they're deploying GDAL as part of their commercial software system.
We've talked a lot on this show about fuzz testing. And I'm finding myself thinking, okay, you've got 200 whatever file formats, however many of them you offload out, but it's pretty well accepted that fuzz testing anything that accepts user input is good practice. Are you like, what does your test scenario look like for all?
So GDAL was, let's see, Evan's not here, but Evan Rualt is the current maintainer and kind of the major domo of GDAL at this point.
Okay.
And so he was invited by Google to include GDAL into OSS fuzz.
Oh, right, sure.
Very early on. And I think we were GDAL was one of the projects with the most findings, for some time window. It was also one with some of the more complex findings. And so GDAL is, so how do I say this? Not every format driver is fuzz tested equally because of this linking and the proprietary things and all this sort of stuff. But the test suite as currently run is fuzz tested with commits to the code base.
Wow.
And so we get findings not as frequently as we were.
Well, yeah, and OSS fuzz is a continuous fuzzing harness, right? Like it's just always running.
Yes. And so, they've found issues in libtiff. They've found issues. I don't think they found any issues in libjpeg, but they'll find little issues, right? And sometimes that originates from GDAL and its usage or just the SDK usage. The test suite for GDAL is very large, but it's not it is testing of capability more so than full engineering tests of every possible path through the code base. It doesn't test that. And the C++ testing in GDAL is actually driven by Python. And so because it's very data sensitive, right? You have all these different data types and configurations. Most of the testing is around that. I wouldn't recommend putting GDAL at the end of your web address and saying, pass me in data, even though it is fuzz tested. And you might want to jail stuff up a little bit.
That's awesome, though. That's really cool.
Yeah.
I don't know what answer I expected, but I didn't expect that. Yes, of course, we're continuously fuzzing as much of it as we reasonably can.
Underlying support libraries for GDAL, like Proj, are also fuzz tested through OSS Fuzz, Proj, and I think GEOS, which would be the geometry algebra engine that you'll also see used. And so, we were the groups in these projects were early participants in OSS Fuzz. Mostly because Google was using them and also wanted to, essentially not have to upstream all the bugs they were finding, right? So like that feedback loop was a lot tightened up quite a bit.
All right. Well, Howard, it was great having you on the show today. Thank you so much for telling us about these libraries. Anything you want to plug before we let you go or anything like that?
So a couple of things I want to plug. One is something called Cloud Optimized Point Cloud and Analysis Ready Data. So in the geospatial realm, you're because the data are so large and they're sitting at rest somewhere, having the data laid down on disk in a way that you can access them without having to process all of them, like we were talking about earlier, is an important thing. And so you're starting to see some efforts to do that. And so one of our efforts on the point cloud space is Cloud Optimized Point Cloud. That's at CppCast.io. And the other is I would never claim to be much of a C++ software engineer. So thank you very much for the opportunity to be on your podcast. I mean, for us, C++ is kind of a means. At the time there wasn't doing high performant geospatial software processing where you want to move lots of bytes around, compress lots of bytes, transform lots of bytes. Like that meant C or C++, and maybe it still does today. But that's how these libraries came into being. And it's been interesting watching C++ kind of continue to evolve over the years to be something certainly quite a bit different and more like other programming languages than it certainly was 20 years ago.
Awesome. Well, I certainly hope C and C++ still do mean high performance and everything like you were just saying. I think it does. Thanks again, Howard.
Thank you very much.